So let's talk constraints. So basically, we now want to start adding constraints again into Lagrangian mechanics, just like we did into the calculus of variations kind of in general. So it turns out that if we're dealing with something which is known again as a holonomic constraint, these are again typically algebraic constraints. Algebraic constraints which only depend on the coordinates. Now, if I have these typically holonomic constraints, ones that only depend typically on the coordinates, most of the time the way we can handle constraint is actually fairly easy in that we choose our generalized coordinates, which now take these things into account. So again, when we were doing that simple harmonic oscillator, in that case we had a holonomic constraint because it only depended then on the position because it was bounded by the length of the object. So in that case, if we chose our 1 degree of freedom, which was defined in terms of the angle, then we don't have to include our constraint explicitly. It's already placed in there because of the generalized coordinate that we're using. So a lot of times the holonomic constraints are most easiest basically just dealt with if we deal with them in the generalized coordinates from the get-go. Another type of constraint we'll see a lot is what's known as a non-holonomic. So non-holonomic constraint. These are constraints that actually depend not only on the coordinates themselves, but on the velocities of the coordinates as well. So these depend both on the coordinates and velocities. Okay. So in this case, we're going to have constraint equations that go something like f of x alpha I, x dot alpha I, and time are all then simply equal to 0. So these are non-holonomic unless if I can find a way to integrate these constraints to basically then get rid of the velocity dependence and have only then a dependence on the coordinate itself, then that's what's known as a semi-holonomic constraint. So here, if we can integrate, to eliminate the x dot alpha I, then these are what we call semi-holonomic. Great. I'm spelling holonomic wrong, but oh well. Sorry. So a particular type of constraint, or at least version of constraint, we'll look at is, say, a algebraic constraint. So if we had algebraic constraints, which looks something like, throwing my chalk on the floor, the sum over I of AI xi dot, so this is the velocity, plus some constant b is equal to 0, where I here is running from 1, 2, and 3. Right? Now, in general, if I had something like this thing cannot be integrated. So in general, cannot be integrated. So this is then going to be equal to a non-holonomic constraint. Unless, for example, b here was equal to the partial of f with respect to t, and then a is equal to the partial of f with respect to x dot, no, just xi, xi, In this case, this thing is going to become then the sum over I of then partial of f with respect to xi times then the derivative term, which is going to be the same thing then as what? The derivative of xi with respect to time, plus then partial of f with respect to time is equal to 0. But this thing here is simply what? The whole thing is simply just the total time derivative of f, right? So here I'm just simply using the chain rule, expanding then this derivative with respect to f, and then this is if it has an explicit dependence on time. So this thing is actually then simply equal to the total derivative of f with respect to time, then is equal to 0. So if this ai here is then equal to some constraint equation, or at least the partial derivative of that constraint equation with respect to xi, and then b is then its explicit time-dependent version. What this means then is that we can write this as a total derivative, but since this is a total derivative, we can then simply integrate it, which means that we can write then f of xi t minus a particular constant is then equal to 0. Okay. Now, in this particular case, this what we thought was a non-holonomic constraint is actually equal to a holonomic constraint. Under this particular integration. Now, the best case scenario is that instead of having an algebraic constraint, well, just say best case scenario, but if we had a non-algebraic constraints, then we can actually use Lagrange's undetermined multipliers that we talked about before. So let's say I had a differential constraint, which is given as the sum over j of the partial of f sub k partial q of j times dqj was equal to 0, where in this case j is running from 1 out to s, right? So again, s is just going to be the 3n minus m, so that's the total number of independent variables I have. K is equal to the number of constraints, so it's going to go 1 all the way out to m, how many constraint equations I have. Now, if it looks like this, we can then easily put this into our Lagrange's equation, which says that we have the partial with respect to qj, the Lagrangian, minus then the time derivative of the partial derivative of Lagrangian with respect to the generalized velocity, plus the sum over k of then some undetermined multiplier, which in general can be time dependent, times then the partial f of k with respect to qj is then all equal to 0. So in this case, if we have a constraint which is given in terms of a differential equation, in that case we can easily add that then to the Lagrange's equation, and now we can solve the dynamics now using this with this undetermined multiplier. Now this portion here, so basically all of this last term here, is usually what's called Q, so capital Q of J. Right, so again, this is simply equal to the sum over K of lambda K partial Fk with respect to partial Q of J. So this thing only depends on J since we're summing over all possible K values. This thing is actually what's known as usually the constraint force. So this is the generalized constraint force. Now, the nice thing again about the Lagrangian mechanics is we don't have to necessarily know what the forces are, but sometimes it's nice to know what those forces are. So for example, if I had, again, something rolling down without slipping across here, and I want to know what was the force which was causing that thing to actually rotate, in this case, that force will then simply be given by this Q term, or again, this generalized constraint force. So this generalized constraint force, a lot of times will actually tell me what the forces are which are generating these particular constraints that I have, even though, again, Lagrangian mechanics does not require me to know what they are in advance. So I don't need to know what these forces are in advance, but again, I can determine exactly what these forces are purely based on the fact that, again, it comes from this constraint equation, where again, I just need to know what that constraint equation is, take derivatives of that, multiply by then these unknown lambdas, and then I can solve for what lambda is. Once I know what lambda is, then I know exactly what this constraint is. So, in the next video, we'll do a bunch of examples of this, basically see how this actually works and talk about some of the constraint forces and etc.